General relativity, step by step. We've got these Kruskal Szekeres coordinates here, and I want to work out what the metric tensor looks like. And I want to work out what the line element looks like. So we'll do that now. You'll remember that I had I'll just pinch in a little bit. You'll remember that I had ds squared was equal to 8 over r e to the r dp twiddles dq twiddles, which is the observation that started all this off. And I've got my relationships here, which is that t equals a half p twiddles plus q twiddles, and x equals a half p twiddles minus q twiddles. And so what that tells us here is that dt squared minus dx squared equals everything cancels out. I've got a factor of 2. Yeah, I've got 2 over a half and another 2 over a half equals 2 dp twiddles dq twiddles, just by squaring and adding and subtracting these two guys here. So the line element here looks at ds squared equals 4 over r e to the r times this beautiful thing here. Which way around have I got it? I think I've got a minus sign missing here. Yeah, that should be a minus, because I've always got minus dt squared plus dx squared. So that tells me that in Kruskal Szekeres coordinates, if that's x and that's t, that tells me that my null light geodesics, which are ds squared equals 0, has got dx squared equals plus or minus dt squared, or dx equals plus or minus dt. So null geodesics are at 45 degrees in this beautiful coordinate system, which is quite a startling observation, really. We've gone through all this rather peculiar mathematical transformation to try and get rid of the pathology at r equals 1, and we've finally, or Kruskal and Szekeres between them, have finally come up with a coordinate system which A, does not have any peculiarity or singularity, coordinate singularity, at r equals 1, but it's also got this nice property that light travels at 45 degrees. That's beautiful. So what I'm going to do in the next screencast is show you what space-time diagram looks. Oh, actually, before I do that, there's just one other piece of information. Let's just go back here and have a look what happens when r equals 0. What does that look like? What does r equals 0 look like? Well, it's not as obvious as it might be. We've got that t equals, well, actually, let's do a little bit of formal analysis here. Let's see what t squared minus x squared is. T squared minus x squared equals, just a minute, I'm trying to scroll across. Sorry, t squared minus x squared, or we square this equation, it's just e to the r, and that's r minus 1. And then we use the fact that cosh squared equals 1 plus sine squared to give us the fact that t squared minus x squared is just r minus 1 e to the r. That's quite nice, because the sine squared, the cosh squared minus the sine squared equals 1. And that's true irrespective of whether whether or not r is greater than 1. So just from this very simple relation, if I specify that r equals 1, that tells me that t squared minus x squared equals 0. So t equals plus or minus x, and this is the representation for r equals 1, which is quite nice. Nice and simple, if any rate. It's maybe not so easy to understand. Now what happens if r equals 0? Well, we've got a rather more peculiar thing, which is that t squared minus x squared equals, e to the 0 is equal to 1, equals minus 1. So that tells me that t squared plus 1 equals x squared. So it's a hyperbola, which is quite interesting, and we'll see that on the next screencast. But for the moment, I just want to stop there. We've got these beautiful Kruskal Szekeres coordinates here, where light travels at 45 degree lines, and we've got these other relationships here, which I'll show you visually in the next screencast. Stop.